chemistry. We are now heading to the lecture that is based on life science, the zoology. So the next speaker is Dr. Sanjeev Sarkar. He will be speaking all the way from the Aortic Research Center, uh, Baylor College of Medicine, Houston, Texas, USA. So it is my pleasure, it gives me immense pleasure to introduce Dr. Sanjeev Sarkar, who is a very young and dynamic researcher. Uh, Professor Anand Mukhopadhyay sir will be very happy to know that he is one of his own student. Dr. Sarkar, he passed his MSc from the University of North Bengal in the year 2010-12, and he did his PhD from jointly from the CSIR, NIST and RMIT University, Melbourne. So he is a very dynamic and a young researcher. He is now presently holding the post of postdoctoral research associate at Aortic Research Disease Laboratory, Baylor College of Medicine, Houston, Texas. He has got immensely worked in the field of nanoparticles, nanoparticle design, synthesis, characterization, stimuli response, drug delivery system, and so on. He is also a recipient of the RMIT International Fee Offset Scholarship, based on which he did his PhD in Melbourne, Australia. He is also a recipient of the CSIR Senior Research Fellow, Junior Research Fellow, UGC BSR Research Fellow, and so many other fellowship he has already received, and he is presently enjoying also. So he has published so many researchers. I'm not going in detail about number and type of researchers publication he has done, but I can say that he has published a number of researchers in Journal of International Repute like Nature publication, etc. So it is very encouraging for a young people like us to follow his path, and that is why I think he is invited here. He will encourage us. He will deliver a lecture. His topic is actually unlocking potential, opportunities and challenges in nano carrier based drug deliveries for managing diabetes mellitus. I think it is his core of research. He is working on this particular field, and actually he did his PhD in this field only, and he is carrying out the research in this line only in USA. So over to you, Dr. Sanjeev, if you can hear me.
Yes, thank you, Dr. Kumar Vasnaj.
Okay, yes, Sanjeev, you carry on.
Yeah, sure, thank you. I'm really privileged to be here with you, and thank you very much, Kumarda, for your nice introduction. And today I'll be talking about
properly actually from your side.
Okay. Okay, just a minute. the development of scanning tunneling microscope was invented, I mean the scanning tunneling microscope was invented, then only the nanotechnology, the modern nanotechnology is going to explode. Because was going to explode. Why? Because this tunneling microscope can see the atomic level. So that's why after inventing this tunneling microscope, then the modern nanotechnology began so fast. Now, when we talk about the nanotechnology, one thing strike in our mind that what is nanomaterial, right? So mainly the scale, the centimeter scale. I mean, when we talk about the centimeter, but when we talk about the nanoscale, then we need to think about that nanometer. You can see here the scale. What is nanoscale? And from 1 to 100 nanometer, the nanoscale is especially 1 to 100 nanometer. And the nanomaterial is called any material which size varies from 1 to 100 nanometer. But sometimes nanoparticle is also considered below 1000 nanometer. So you can see at the left panel, there are some molecules, some biological molecules like hemoglobin, GNA, and this biological molecule, these are in nanometer scale. And the right hand, you can also see some one glucose molecule and viruses. The glucose molecule is 1 nanometer scale. 1 nanometer. On the other hand, the virus is 100 nanometer. So in this scale, any material is called nanomaterial. Actually, this material which was synthesized by ourselves. Now, here you can easily understand the size of a particular cell, like lung epithelial cell. You can see this is a lung epithelial cell, and which diameter is 15,000 nanometer. At the right side, you can see the other cell, which is also a lung epithelial cell, whose size is 10,000 nanometer. And inside the cells, there are numerous black spots, you can see, and which are indicated by arrowhead. And these nanoparticles are accumulated, are internalized into the cells. So you can easily understand the size of the nanoparticle, which are very, very minute compared to the cells. When the talk about the nanoparticle size, these nanoparticles are sometimes below 10 nanometer. And when the below 10 nanometer, and there are some special type of nanoparticles, and which can also emit fluorescent light when it absorbs lower wavelength of light, like UV light and X-ray or infrared light, lower wavelength light, and it can emit higher wavelength of light. And these nanoparticles are called quantum dot. You know very well that recently in 2023, the Nobel Prize in Chemistry was awarded for the discovery of quantum dot. And if the quantum dot size is less, like 2 to 3 nanometer, then it can emit the light blue or green. And when the size is increasing, that is like 5 to 7 nanometer, these nanoparticles gave yellow to orange, then red color. So the size of the nanoparticles matters. Because when size changes, when the particle size, any material size comparatively lower, I mean in the nanometer range, the property of the particle is changed. You can see here how due to the change of some nanometer, they give different colors like yellow, orange, red, like that. So for synthesis of the nanoparticle, there are two main aspects. There are two main approaches, like top-down approach and this bottom-up approach. So top-down, that means there is a bulk material, there's a large material. You need to literally break the material to small pieces and then synthesize the nanoparticle. On the other hand, the bottom-up approaches are the totally opposite approach. That means you need to gather small molecules to form nanoparticle. So there are several methods to gather these nanoparticles, like spinning, like Solzen process, laser pyrolysis, chemical vapor deposition, molecular condensation, etc. Now, in the real-time example of top-down method, I think you've heard about the 3D, 3D scaffold, 3D structure, like somebody talk about the heart, artificial heart or kidney, all these things. These are produced by top-down approach. And on the other hand, bottom-up approach, like all the drug delivery vehicle, drug delivery carrier, these are very, very small. And this type of nanoparticles, this type of nanomaterials formed by the bottom-up approach. So for example, lipid nanoparticles, silicon nanoparticles, and carbon nanoparticles, all this. See, here are the different types, different shapes of nanoparticles. Uh, Researchers are keen to synthesize different types, different shapes of nanoparticles, and depending on the size, their property is also changed. This is the mystery of the size. Also can denote the property of the nanoparticle. It may help. Sometimes it may help to internalize into the cell some nanoparticle like nanotube. It may help in different function, and some nanoparticles are gender-like structure. These are for different purposes. So the different shapes of nanoparticles for different purposes. Here you can see the real-time image, like a transmission electron image of spherical nanoparticles, prism-like nanoparticles, nanobar, and this is nanowire, and this is the nanocube, nanopyramid, nanorise, and nanoflower. So the nanoparticles you think about to delivery of the drug to specific area, specific site. So target is the main thing, right? So for the target of the nanoparticle, you need to functionalize, you need to modify of the surface of the nanoparticle. For the surface functionalization, there are plenty of molecules available, and one of the example is peptide or protein. Sometimes it may be the nucleic acid, sometimes it may fluorophore, sometimes it may antibodies, right? And surface chemistry like charge, chelator, and other chemical molecules also important for shaping, for preparing the nanoparticle for targeted or stimuli responsive drug delivery. So when you talk about the nanoparticles, so somebody think about that a nanoparticle, is it present in our body in any molecules or anything in nanometer scale? Yes, answer is yes, because our biomolecules like protein, RNA, DNA, all are nanoscale size, and they're also interact with the other proteins like in the mitochondria. You can see here, this is the mitochondria, and in the mitochondria there is a chemistry, and in the chemistry there is a ATP production site. There is actually it is called electron transport system. So in this electron transport system there are some proteins, and these proteins help, and these are also the nanoscale size, and these are this help to generate energy in mitochondria. And so this nanostructure, our nanostructure can easily interact in the cells with the nano scale size, nano size biological molecules. But it is easy to talk about to delivery nanoparticle in a particular size, right? In the human body or animal body. But the problem is there are some biological barrier inside the body. Like one is mononuclear phagocyte system. Second is um, non-specific distribution of nanoparticle. Third is hemorrhagical limitation. Fourth is suppose it is you are doing you are trying to deliver drug into cancer patient. So there is intratumoral pressure, and sometimes endosomal escape is also a barrier, and the multi-reactor resistance. Sometimes the nanoparticles are thrown out of the cells. So this is the biological barrier, and which need to be overcome when you deliver the nanoparticle in the body. So to synthesize the nanoparticle and deliver in site-specific manner, and to overcome the barrier, we need to keep some parameter in our mind that your nanoparticle size, shape, and the charge. Here you can see the different size of nanoparticles, and it is deposited. It is retained by the sometimes by lung, sometimes liver, spleen, and kidney. When the size is around 20 to 150 nanometer, the retention by the lung, liver, or kidney are comparatively lower. And when you talk about the shape, this spherical shape is the most preferable shape for the nanoparticle for drug delivery. And the charge, if we talk about the charge, it's if it is neutral or it is negatively charged, it's good for drug delivery, because this nanoparticle with negatively or neutral charge, these are easily overcome the biological barrier. So now the question is, what is nanomedicine, right? So nanomedicine is anything like diagnostic and like any nanomaterial or device which help in diagnosis or imaging or treatment, and most importantly, the safety, right? The safety is always the first priority. So nanomedicine can be used in different biological fields for different disorders, different diseases, like neurodegenerative disease, cancer, atherosclerosis, pulmonary arterial hypertension, myocarditis, and rheumatoid arthritis, inflammatory bowel syndrome, hyperthyroidism, and diabetes. So nanomedicine application is not so new. It is initiated when it was Greek, Greece space was approved by the FDA. FDA is the an American the, Food and Drug Administration. This is a regulatory body of America which approve any kind of drug. So this every approved this Greece base for the first time for the tumor infection therapy. And in the 1990, and ambiosome is the first nanoparticle approved for intravenous administration for fungal infection therapy. And then Toxil, the first physiologized nanoparticles approved by FDA. Like on this nanoparticle, lots of nanoparticle was approved by FDA and applied in the animal model, in the human body. And recently, you are all are witnessed that the COVID, right? So COVID vaccine. There are two vaccines in America, that Pfizer and Moderna vaccine. These two vaccines are RNA-based vaccine. Do you know that which is the carrier of this RNA-based vaccine? Yes, this is the nanoparticles. This is the lipid nanoparticles, liposomes, and these liposomes were able to deliver mRNA to the cells, to the blood, and that gives the American people or the people which took this Moderna vaccine this protection against the coronavirus. Now I'm going to detail and diabetes, drug in diabetes. If you see the global scenario of diabetes, 1 in 11 individual is diabetic in the all over the world. You are readily got surprised that in India, 1 in 7 individual is means, diabetes patient. Then, according to the International Diabetes Federation 2021. So we need to think about it. We need to search the method of treatment by which we can reduce the future diabetes, right? Now, the problem of the conventional treatment strategy is the 50% of the diabetic patient cannot control their blood sugar level. So, what is the possible way out to manage the diabetes? If this hyperglycemia stay for a long time, there are multiple diseases can occur in our body, like cardiovascular disease, like um, uh, and kidney disease, renal disease, that is diabetic retinopathy. On the other hand, if you have very low sugar in your body, sometimes you can feel the unconsciousness or even death. So the normal, the current treatment strategy, which we usually use the insulin injection, right? It cannot properly maintain. Here you can see the graph. Here, the insulin level, normal insulin level, and current and physiological insulin needs and current insulin therapy. It is always greater than the normal level. So normal need. So due to use of this external insulin, we got insulin resistance. So what are the possible way to overcome this problem? There is a astonishing, there is a very promising process, very promising approach, that stimuli responsive drug delivery. For stimuli responsive drug delivery, like pH responsive, mechanic responsive, light responsive, temperature, electric, ultrasound, enzyme, and most importantly, glucose responsive drug delivery. The glucose responsive drug delivery depends on three things. Like, one is glucose oxidase, which is a glucose sensitive molecule. Second is glucose binding protein, like concavalin A. This is also a glucose sensitive molecule, and another is phenylboromic acid. So I will talk about it in detail. So before that, you need to know that what are the current situation and the progression of the diabetes. There are three major phases. One is primary prevention. That means beta loss is beta cell, and the beta cell in the pancreas is almost will just start to degrade, or it is stable. But in the second phase, it is start to degrading, and third phase it is almost degraded. So we need to think in different stages and different treatment strategies, right? So in the primary prevention care, we need to check the beta mass. Beta mass. That means beta cells is restored or not. Beta cell is damaging or not. We need to monitor in the first phase. In the second phase, we need to check the glucose level. Third phase, we need to add insulin. So we need to prepare the novel insulin, because all time, if you get the normal injection, and in a day 2 or 3 times, and daily you are taking injection, and then you are getting the insulin resistance, so it need to be careful, right? So there are glucose-based, there are glucose sensor technology, like particle, when nanoparticle is attacked with a glucose oxidase, then it interact with the glucose, and in the glucose, it produces gluconic acid. That means acid and hydrogen peroxide, and it also produces hydrogen peroxide, and it can be detected, by which this glucose amount can be detected from the blood. And other glucose sensors molecules are here, like boric acid and cancavalin A, that is con A, and some fluorescence check nanoparticles are there by measuring the fluorescence, that is higher light. You can monitor the glucose level, and on the other hand, indirect ratiometric method and amperometric method, here you can measure the charge of the ions, especially ions in the blood. And especially when we talk about the glucose responsive delivery, the mechanism of the glucose responsive delivery is this phenylboronic acid. When it is take this phenylboronic acid and the glucose, when the glucose and phenylboronic acid attach, and when new glucose molecule come, and this new glucose molecule join to the nanoparticles, and the insulin, which is previously attached to the nanoparticle, is released. And in a concovalent triggered release, this is a concovalent protein, and this is, as I told you, that is concovalent protein is glucose sensitive protein. So when it finds the glucose, it attaches the glucose and release the insulin. And other is glucose oxidase. Glucose oxidase trigger release. That means here also when the glucose is present, that means this glucose oxide produces gluconic acid, that is lower the pH, and the lower the pH, that means the insulin are positively charged, the insulin get detached from the nanoparticle. And some other methods are there, like glucose mediated swelling, glucose mediated degradation. Now, I'm especially detailed in the mesoporous silicon nanoparticle based delivery of antidiabetic drug. So why mesoporous silicon nanoparticle? Mesoporous silicon nanoparticle has numerous advantages over other nanoparticles, like biocompatible. This is a biocompatible, and tunable. This is a tunable size and pore, and excellent stability, glucose sensitivity, and easily excreted out from the body, functionalizable, and high surface area and pore volume. So this mesoporous silicon nanoparticle are already approved by several forms, like Cornell dot. This is a silica sphere, not a mesoporous silicon nanoparticle. This is a silica sphere which is approved for several years ago by the FDA, and amorphous silica is also approved by the FDA. Now, in our laboratory, we synthesize mesoporous silicon nanoparticle. This mesoporous silicon nanoparticle is was synthesized by the molecule called TOS-tetraethyl silicon, and the surfactant is CJAP. And by this surfactant, we form the structure of the nanoparticle, and actually it is to form the pores of the nanoparticles. And finally, after refluxing, this pore is created, and this spherical nanoparticle was made. Here you can see the functionalization. As I told you, the functionalization of the nanoparticle is very much crucial. That is why we functionalize the nanoparticle with phenylboronic acid. This is the key molecule. This is the major molecule which was attached to the surface of the nanoparticle and make the nanoparticle glucose sensitive. And then we load vitamin D and vitamin K. Why vitamin D and vitamin K? Vitamin D and vitamin K has anti-diabetic effect, and most importantly, they are lipid soluble. That means they are not water soluble. So most of the drug, about the 40% of the commercial drug are lipid soluble molecule. So it is very easy to give any drug which is water soluble and which can be easily absorbed by our body, by our intestine. But in case of lipid soluble drug, it is very difficult to deliver the drug. That is why we select two vitamins, vitamin K and vitamin D, for this purpose. So after formation of this nanoparticle, we loaded vitamin D or vitamin K in the nanoparticle pore. Here you can see this is the nanoparticle. These are the nanoparticle pores, and in the nanoparticles pore, we loaded the vitamin K or vitamin D, and then the pore of the nanoparticles are closed by dextran. This is a carbohydrate polymer. You see, this dextran is bind to the phenylboric acids by the covalent bond here. So these phenylboric acid and dextran bond bind each other, and the pores are closed, and this the drug get entrapped into the nanoparticle. So after this, we did some characterization of the nanoparticle, and we find that our nanoparticle was spherical. Here you can see this is a transmission electron microscopic image. This is a high, especially the high resolution transmission. Sorry, this is a field emission scanning electron microscopic image. You can see the nanoparticle, the surface of the nanoparticle is very smooth, and these are the spherical in shape. Here you can easily see the figure A. This is a high resolution transmission electron microscopic image. Here, image A, you can see the multiple pores in the nanoparticles. And inside these pores, we loaded the drug. We loaded vitamin K, vitamin D, and then we kept the nanoparticles pore, nanoparticles pores by dextran. You can see the surface. The surface is not like the previous one. It is the nanoparticles pores are closed because due to presence of dextran. This is the coating of dextran, and this dextran coat entrap the drug and keep the drug inside the nanoparticles. And after this is after K loading and dextran coating, and this is after vitamin D loading and dextran coating. You can see the PDX of this. The different atomic weight and percentage of atomic weight and all the atom weight. And now the release mechanism, how the vitamin K and vitamin D was released from the nanoparticle. As I told you, this phenylboric acid, that means this violet color, this is the phenylboric acid on the surface of the nanoparticle, and this phenylboric acid is glucose sensitive, glucose responsive molecule. This glucose responsive molecule, when find the glucose, this 1,2 diol of the glucose molecule is interact with the phenylboric acids, this bond, and these bonds are brought due to the interaction with this 1,2 diol of the glucose molecule, and this glucose molecule joined here, and the dextran molecule released from the here. I didn't show here with the dextran molecule, but a dextran molecule was released from the surface of the nanoparticle, and the glucose molecule bind to the phenylboric acid. And see here this drug is coming out from the nanoparticle spore. So for glucose sensitive release, we measured the amount of vitamin K and vitamin D which are released in different glucose concentration. You can see here in the graph A, this is a vitamin K release, and B is vitamin D release. We choose different glucose concentrations like 11 nanomolar, millimolar, and 25 millimolar. Why we choose this glucose concentration? Because this 11 millimolar is similar to 200 microgram per deciliter, that is DL. That means if you go up to the over the 200 nanomolar, 200 mg per DL, that is 11 nanomolar, that is your diabetic patient. So this is the borderline, right? And this is 25 millimolar is used for to mimic the diabetic condition. That is, it is 450 milligram per DL. So in this condition, I mean a 25 millimolar condition, the release of vitamin K and vitamin D are significantly higher compared to 11 nanomolar glucose concentration. And you can see here in 0 millimolar of glucose, there is no release at all. So, so cytotoxicity is the key issue of use of nanoparticle. Therefore, we use cytotoxicity assay to determine the toxicity of nanoparticle. Here we find in the two types of cells. One is C1 and another is C2C12. That is, one is muscle cell, another is mammalian liver cell. Both are mammalian cells. And we found that up to 200 microgram per ml, there is no significant cytotoxicity in both cases, in low glucose and in high glucose condition. Here you can see the confocal microscopic image. Here, the left panel is for DAPI. We, as our nanoparticle was tagged with fluorescence, that is FITC. The nanoparticles was tagged with FITC. That is why nanoparticle gives a fluorescence color when it is under any UV radiation or laser beam. If you give on this nanoparticle, then it will show the fluorescence. So for cellular uptake, that means the nanoparticle is going to cells or not, where we check that and we find that nanoparticles, you can see here, this is the right panel, the middle panel is for nanoparticle only. This right panel is, you can see the nucleus, and surrounding the nucleus there are multiple of the nanoparticles are accumulated into the cells. That means these nanoparticles are entered into the cells. Here, flow cytometric study also proved that nanoparticle is entered into the cells. You can see here, we measure the population of cells which uptake the nanoparticles. Here you can see 97.7% almost took the nanoparticle. I mean, this mass of the population of the cells took nanoparticle. Here you can see the nanoparticles which are RITC tagged and vitamin D loaded nanoparticle. We also checked this type of nanoparticle and their cellular uptake. We find the similar result. You can see here the red spot. That means you can see very clearly that red fluorescence are inside the cells. That means you can see, if you see the March image, you can see this confocal image. You can easily understand that nanoparticles were inserted into the cytoplasm of the cells. Here, this is the liver cell, that is hepatocyte, and upper one is muscle cell, that is myocyte. And similar results were found in flow cytometry. Here you can see 76.33, here 46.98% of cells uptake this nanoparticle. And we also checked, after checking this cellular internalization, we checked is that after entered into the cell, the nanoparticle released vitamin K or vitamin D. Then we checked the level of vitamin K and vitamin D. Actually, we extracted the cell and isolate vitamin K and vitamin D, and these two vitamins were measured by HPLC, and then we found that in different glucose concentration, like 5.5 millimolar glucose concentration, this is a low glucose concentration, and then 5.5 millimolar glucose concentration with the nanoparticle. Here you can see this figure 1 bar diagram, figure A, you can see here this when we add this nanoparticle 5.5, 11, and 25. This is the glucose concentration. We added the nanoparticle in the cells when cells were treated with different glucose concentration. So in high glucose concentration, the nanoparticle were released higher amount of vitamin K and vitamin D in both myocyte and hepatocyte. Here we used only the myocytes in case of vitamin D. Then we checked the vitamin K to reduce glucose level or glucose uptake in the cell, especially in myocyte. So we used 6-NVDZ. There is a glucose analog, and it cannot be converted to the glucose end product. That's why it will be, if this 6-NBDZ uptake by the cell, and it will be stored in the cells, and it can easily measure this fluorescence glucose 6-NBDZ glucose analog. So we measure this glucose analog, and we find that when we treated the nanoparticle and treated the cells with high glucose concentration, like 25 millimolar glucose concentration, we find the significantly higher amount of 6-NBD, that is a higher number of glucose. That is, glucose uptake was significantly higher than when we treated the vitamin K loaded nanoparticle. Here you can see the glucose expression. We know that the glucose is uptake by some protein which is located on the surface of the cells, and actually these are remain sometimes in the cytoplasm, and they transport to the cell plasma membrane. So we measured the GLUT4 expression in the muscle cell. So GLUT4 expression, that means it indicates if the GLUT4 expression is higher, comparatively higher, then it means that it is present in high concentration and it can uptake higher amount of glucose. You see here, we treated the cells with high glucose. When we only treated the cells in high glucose, comparatively normal condition, it is comparatively, the expression is comparatively low, right? So because due to the maybe due to the it is mimicking the diabetes. In the diabetes, we know that the glucose cannot be uptaken by the cell, taken by the cells. So that's why in the high glucose concentration, the expression of the glucose is comparatively lower to the control. And when we add only vitamin K, and a little bit GLUT4 expression was increased. But however, when we use vitamin K loaded nanoparticle, the GLUT4 expression is significantly higher. That means the same amount of vitamin K cannot increase the GLUT4 level in the cells. On the other hand, the same amount of vitamin K, when it is in the nanoparticle, it increases the higher amount of GLUT4. That means the nanoparticle is also increase the bioavailability of the vitamin K. That means it can easily enter into the cell, and it can release the vitamin K into the cells. And that is why the more number of vitamin K molecules are entered into the cells, and higher GLUT4 expression we observed. Here, similarly, we can we find the similar result. Here you can see in control, I mean the low glucose and low glucose plus nanoparticle, there is no significant difference in GLUT4 expression. Here you can see in the figure B, the black and red one, there is no significant difference. However, when we use high glucose concentration, the GLUT4 level is significantly lower. But in high glucose and vitamin D, and this is increased slightly, but not significant. But when we use vitamin D loaded nanoparticles, then this vitamin, due to presence of this nanoparticle, GLUT4 expression was significantly higher. This also signifies.
Sorry
Yes.
to disturb you. We are running actually late. You may now come to the
Yes,
conclusion part.
Yeah, sure. Yes, I'm about to finish.
Okay. Thank you.
So similar result we found the GLUT4 expression when we do this immunoblotting. So in case of immunoblotting, you can see, and when you use the vitamin D loaded nanoparticle, the GLUT4 expression was significantly higher. And we did this animal study, and we fed, we oral gavaged the mice with the nanoparticle, and this is the mechanism. And we oral gavaged the nanoparticle, and nanoparticle entered the blood, and then in the blood, due to the high glucose concentration, this dextrano was released in the blood, and then nanoparticle interact with the cells, and the cells get the nanoparticle, and then inside the nanoparticle, the vitamin K was released, and after that, nanoparticle was exercised from the cells. So in animal study, we measured GLA protein, which is the marker of vitamin K. So we find in the muscle and liver both are significantly higher. That means vitamin K was reached in muscle and liver. And we also found that blood glucose level was decreased significantly when we use this vitamin K loaded nanoparticle. And in other group, there is no significant difference. So we also did this histological study. We found that when we use the vitamin K, actually in diabetic mice, you can see some abnormalities in the muscle, thinning the muscle fiber, and in the liver tissue also there's some abnormalities, and which were recovered when you use silicon nanoparticle with vitamin K. So our future direction of this study, and we can say this, we will do in and long-term animal study, and we will definitely do in the adipocyte as well, and this should be come into the clinical trial, and after clinical trial we will think about further. So there are some challenges in the studies in the nanoparticle drug delivery, and especially the regulatory issues, like human health, the potential toxicity in the human health. That's why you need to take care about the toxicity of the nanoparticle. You need to do the long-term animal study before entering the clinical study. And the scaling up is also the challenging when you increase the scaling up, then the amount of production. I mean, then you have to maintain all these conditions same, and then the reaction volume and all these things should be the same, and then you can easily get the product in high quantity. So these are my some copy of essay publications. So I would like to thank my supervisor, PhD supervisor, and all my lab mates in PhD lab, and I would like to thank my my supervisor in postdoc lab. Okay, thank you.
Thank you. Thank you, Dr. Sanjeev, for your illustrious presentation. We enjoyed a lot here in India. You are still awake. In US, it is. I know it is almost midnight or past midnight. You are still awake for us.
It's yes, it is 2:30. 2:30 in the USA.
Thank you so much. In future also, we'd like to have you with us. Okay, thank you. So now I request Dr. Jyotsna Das ma'am to kindly introduce.
Okay, thank you, Kumar.